Hi guys, recently we have been looking at the different carbon molecules such as aldehydes and ketones, and today we're going to be looking at the importance of these molecules in the flavours of food. So first of all, to understand the chemistry of food, it's important to look at the molecules responsible for the flavour in food. For example, limonene is found as a flavour molecule which is found in lemons. We've got furaniol, which is a flavour molecule found in strawberries. Vanillin, the flavour molecule found in vanilla pods. And capsaicin, the flavour molecule which is found in chilies. So capsaicin is responsible for the burning sensation that we feel when we eat a very spicy meal. So for example, if you're eating capsaicin and you try to get rid of that spicy, of that hot flavour by washing your mouth out or rinsing your mouth out with water, capsaicin we find is actually quite a non-polar molecule due to the big parts of the molecule which are non-polar. Although it does have some polar groups such as your NH and your OH, overall we find that this molecule is actually non-polar. So it will only dissolve in other non-polar liquids. So the best thing to do to get rid of the capsaicin flavour molecule, which has given you the burning sensation, is to drink milk, which is also non-polar, so that the capsaicin flavour molecules will dissolve in the milk and therefore take away that burning sensation. Another food to look at is asparagus and broccoli. So asparagus, their flavour molecules are soluble in water. And because like dissolves like, if you cook asparagus in water, the flavour molecules from the asparagus will come out of the asparagus into the water, leaving your asparagus flavourless. So you want to cook your asparagus in oil because oil is non-polar, which means the flavour molecules in the asparagus will not want to dissolve in the oil and they will stay in the asparagus. Broccoli is actually the opposite of this. So broccoli flavour molecules are soluble in oil. They're a non-polar flavour molecule soluble in oil, and that is why it's best to cook broccoli in water so that the flavour molecules which are non-polar in broccoli do not come out of the broccoli and dissolve into the water. They will stay in the broccoli. The kinds of questions that you would be confronted with we are going to go through just now. So if you want to pause the video and go through the questions, and then we'll go through the solutions together. So question 10 suggests if the following molecules should be cooked in oil or water. Now when we are talking about this, we know that water is polar and oil is non-polar. So what we're actually considering is our whole like dissolves like. And we don't want to cook our food or our flavour molecules in the same solvent, so the same polarity of a solvent as what they are. So something polar, you don't want to cook that in a polar solvent such as water. Something which is non-polar, you don't want to cook that in a solvent such as oil, because your flavour molecule will leave your food and dissolve in that substance, and it will leave your food flavourless. So if we look at this molecule A, this is a very non-polar molecule. It's made up of just carbons and hydrogens. So each of our little points in our stick diagram here represents a carbon. So I'm circling all the carbons here. And remember that each of those carbons needs 4 bonds, so they'll have hydrogens coming off them. So this is a very non-polar molecule, which means it should be cooked in something which is polar to stop the flavour molecules from escaping. So it should be cooked in water. For B, we now have a small flavour molecule. We have an OH and a C double bond O. Those are slightly polar. Well, your OH is very polar, C double bond O is slightly polar. Therefore, this whole molecule would be a polar molecule. We want to cook it in something the opposite polarity as itself. So we want to cook it in something which is non-polar, so we would cook it in oil. And lastly, we have vanillin, which is found in vanilla pods. And if we look at this molecule, we've got an OH, which is very polar. We've got a C double bond O, which is very polar, which would make this molecule all over polar. So this molecule is polar. And we want to dissolve it, or we want to cook it in something the opposite polarity as itself. So something non-polar, so oil.